Hi class, we are well into chapter 8, or we're really beginning chapter 8, and chapter 8 is all about factoring and quadratic equations. And this section 8.1 is we're looking at factoring monomials. So we remember what monomials are, and when we talk about factoring them, there's a couple of concepts that we need to keep in mind. The first vocabulary word and the second vocabulary word are as follows. The first one is factored form. So factored form of a monomial is really taking a monomial and writing it down in all of its bits and pieces. For example, if I had the monomial, let's say 12xy squared. According to this definition, it says that you want to express the product of primes. So I want to write 12 as only prime numbers being multiplied together and variables. So I'm allowed to have variables, but no variable is to have a power greater than 1. Let's see how we can do that. Well, we remember how to do prime factorization. Hopefully we do. I'm going to take 12, I'm going to prime factorize it. Think of two numbers that multiply to give me 12. Let's say 3 and 4. Since 3 is prime, I'm going to stop there with that branch, but 4 is not prime, so I continue to factor it until I get to prime values. So when I write down the prime factorization of 12, I can write it as 2 times 2 times 3, or 2 to the second power times 3. I hope this is ringing a bell. So that's the first part of this answer. I'm going to write it as 2 to the second power times 3. But wait, the variable has to be written down with only a power of 1. And this is pretty simple. X already has a power of 1, so that's fine. Y to the second power must be broken down to y times y. So each of those have a power of 1. So we've just done prime factorization with a monomial. So that's not too bad, hopefully. The next word that we're taking a look at, or the next term, is the greatest common factor. And you guys remember that. Like you might have the number 12 and the number, let's say, 15, and you're looking to find what number is the greatest common factor. So I think in the past you probably did factor rainbows. 1 is a factor of 12, 2 is a factor of 12, 3, 4, 6, what else do we have? 3, 4, 6, and 12. And then you would write down the factors here the same way. 1, 3, 5, and 15. And you would look for the greatest among these factors. And in this case, the greatest common factor is the greatest factor that they have in common. It's 3, right? Remember it? Well, we're going to, when we find the greatest common factor of monomials, we're going to use the breakdown. Oops, sorry about that. We're going to use the breakdown like we did up here in terms of writing it in factored form to do so. So definitely stay tuned for that. So let's take a look at this next example. Example 1, we're working with a monomial in factored form. We're going to factor the following completely. So thinking through what makes 20, I'll say 10 times 2, 5 times 2, 2 times 2 times 5. I think those are all primes, so I'm done on that account. So 2 times 2 times 5. And then with the x, I'm just going to write the x. Since it's x to the third power, I'll write that 3 times. And since that's y to the second power, I'm going to write that twice. Here's the factored form. I think it's sufficient to say 2 to the second power times 5. And then you could leave the x's written out like that, and then the y's written out like that. So that's really all that we need to do with factored form. Here we're going to talk about finding the greatest common factor of a set of monomials. Okay, so we're going to find the GCF. What we need to do is kind of have a mental picture of what the greatest of what the factors are. But instead of doing it the way that we did when we found all the factors of, I think we just did the example was finding the factors of 15 and 12, what we're going to do is actually see what the number is made of. So I do want you to pay attention to this. If I have 12 a squared b squared c, I can obviously write that as 2 times 2 times 3, right? So 4 times 3 factored out, times, I'm going to write all my a's out, and I'll write my b's out, and I'll write my c. I'm going to do the same thing with 18a b to the third power, right? So 18 is the product of 2 and 9, and that really gives me 2, 3, 3, right? Because those are prime values, times a, times b, B, and B, and there's no C. So what we need to do is find the greatest factor that's going to divide into both of these. And usually, like I said, we would write out all the factors, but here's what we're going to do. Using prime factorization is super helpful because what I need to do is just see what they have in common. Both of them have a 2 in common, right? So I'm already going to start to build, in a sense, my GCF, all right? So both of them have a 2 in common, so a 2 will be included. Do both of them have another 2 in common? They don't. So this one has a 2, but this one does not. So that's not going to work. What does having two 2's as a factor means? It means that 4 goes into it. 4 goes into this number, but it doesn't. 4 goes into 12, but it doesn't go into 18, right? So it makes sense not to include two 2's. But I can include a 3 because they both have a 3 in common. What does it mean to have 2 and 3 as a factor? It means that 6 divides evenly into that, and you realize that that's true. We're going to continue on. I'm going to add an A because A is found in both factors. And then I will put one B in. Then I'm going to have to put another B in because it looks like B's, there are 2 B's that are included. And now there's nothing left in common. So the greatest common factor of these two terms is going to be 6AB squared. All right, so what I've done is basically, so if you look at these numbers without factoring it out, you can see, okay, what number goes into 12 and 18? 6. What value can I see that they have in common in terms of A? Only one A is in common. What do I have in common in terms of B squared and B to the third power? B squared. And finally, the C is not a common factor for both. So this is our greatest common factor. All right. If you want me to explain that a little bit more, because I know it looks a little weird, and I think that you probably were not trained to do that in that way, we can talk a little bit more about that as well. Let's take a look at another example of finding the greatest common factor. Identical bouquets need to be created out of 20 tulips and 30 white roses. What is the greatest number of identical bouquets that can be made without any flowers being left over? How many of each flower will be in each bouquet? So this is kind of a weird question, but really ultimately what it comes down to is you're looking for the greatest common factor, right? Because what you need to do is find a way that you can divide 20 tulips and 30 roses such that you can make those equal number of bouquets, right? Because you need to make sure that you use them all, and you make sure that each number is divisible by the same number. So what we'll do is we'll look at the greatest common factor. To find the greatest common factor, what we're going to do is simply factor it out. But we want to, instead of finding all the factors, we're going to do prime factorization. So prime factorization here would give me, I think we did this one before, right? 2 to the second power times 5. And prime factorization here would give me 2 times 3 times 5, right? And so as we look at this, I'm going to write out, I don't usually always write that out, but I'm going to write this out in this way so we can see what they have in common. So what do they have in common? Well, for the GCF, we realize that they definitely have a 2 in common, and they definitely have the 5 in common, but there's nothing else in common. So 2 times 5 is 10. Our GCF is 10. So that tells me that there will be 10 bouquets, right, of flowers. That's the most that we can do. And now the factors that are left over tell me how many of each type of flower I would have in the bouquet. So let's think about this. Remember, these were 20 red tulips. And then over here we had the 30 roses. And so what we're thinking about is if I took 20 tulips and I divided it by 10, I would have 2 for each bouquet. If I took 30 roses and divided it by 10, I'd have 3 for each bouquet. So how many of each flower will be in each bouquet? We'll have of the tulips, we'd have 2, and of the roses, we'd have 3. All right, I hope that made sense. I look forward to talking to you in class if it felt uncomfortable, and we'll get it together. I will see you guys soon. Bye-bye.